Some of the hardest problems in the world exist far above the planet. Our job? To launch the smartest solutions, to protect our satellites, clean up our clutter, to propel breakthroughs in propulsion, to learn more about our place in the universe, to outpace emerging threats. Every day, the Aerospace Corporation uses the latest technologies to ensure our nation's safety and leadership in space.
Hi, and welcome to the Space Policy Show. As always, you can find us on Twitter using hashtag the Space Policy Show, and you can engage with our experts on Vimeo in the chat box. We would also love it if you would sign up for our news alerts at aerospace.org/policy. Today's episode is on rethinking capability development for the space enterprise with Erin, Ryan, and Alli Taylor. The defense space environment is ever-changing, and we need to engineer space systems to be adaptable to those changes. Today, our host, Alli Taylor, will talk to author Dr. Erin Ryan about a new approach she's developed called Design for Principles, or DFP, a model that can meet the increased complexity and uncertainty of defense space. Erin is a senior project engineer in Aerospace's Defense Systems Group. He joined us after 26 years in the Air Force, heavily engaged in the systems engineering lifecycle. Erin holds a PhD in systems engineering from the Air Force Institute of Technology. Alli is currently a senior project leader in Aerospace's Human Exploration and Spaceflight Division. Her areas of expertise include systems engineering, space architecture strategy, and satellite operations. Alli holds a master's in space studies from the University of North Dakota. Over to you, Alli, to get the show started.
All right. Well, thank you, Rebecca, and I'm excited to be here today. I'm Alli Taylor, and I'm here with my colleague, Dr. Erin Ryan. Erin is going to take us through his Designing for Principles framework, which, Erin, you really, in your policy paper, break this down, getting to some of the core, fundamental, and critical challenges in the world of systems engineering and the space enterprise. So can you give us a quick overview of what is Designing for Principles?
Sure, of course. So one way to think about Designing for Principles, or DFP, is that it's really a competitor to systems engineering in the sense that it's another capability development approach, but it's very different than systems engineering in the sense that it's much better suited to dynamic and uncertain environments. So from a top level perspective, you can think of systems engineering as being very requirement driven, very system centric, and largely focused on technical performance. Whereas Designing for Principles is much more objectives driven, capability centric, and focused a lot more on certain design principles and speed of delivery.
Okay, great. And you also sometimes shorten it to DFP, right? So if we mention DFP, we're really talking about Designing for Principles here.
Yeah, exactly.
And can you tell us a little bit, like, why now? What's the importance of this? Why is the timing right?
That's a great question. There's a lot happening right now, and the phrase that comes to my mind is kind of cliche, so I'm hesitant to use it, but I will anyway. It's an inflection point. There's so much happening right now that's so critical in space in terms of opportunities and threats. And I think it all begins with this hard point, this truth that we all have to recognize, which is the US is on a path to lose its historical dominant role in space. I suspect that doesn't come as much of a surprise to this audience, but it bears emphasizing this because honestly, our potential rivals are not just nearing parity in some cases for some space capabilities. They're already surpassing us or on a path to do so. So that's pretty sobering. And I think that there's a quote from the CSO and the CSO planning guidance that talks to this point really well. He says something along the lines of, we have to adapt to outpace our rivals or we're going to lose our advantage. And that's what's happening. So bottom line, I think that right now, from a capability development perspective, we are going way too slow, like order of magnitude too slow. And so whereas systems engineering has historically been great at delivering exquisite capabilities, Largely, that's been the case when the environment is very stable and predictable and we can respond accordingly. But really, that's not the situation that we're in right now. That's not the future we're likely to face. So I think that's a big part of this inflection point right now. But the other really big piece that we all are aware of is the US Space Force has stood up. It's been a year now. We've got to start making some significant progress in delivering those capabilities so that we're not outpaced by the adversary. And so really I think a generational opportunity to change here with the stand up of the Space Force and the fact that it's a lean, agile force that values more innovative, bold approaches. And I think that's where DFP can really.
And we have a new administration coming in right now too, so I think that's part of the timing. And
Yeah.
so, but this idea isn't totally brand new, right? It's some different parts that you've pulled together. Can you talk about kind of where this came from?
Sure. A lot of sources, honestly, that go back years, starting with my dissertation work over a decade ago that was all about design flexibility. And as part of that research, I came across this idea that had a few different names in the literature. One of them was designing for adaptability, DFAD. Another one was designing for changeability, DFC. And it was one of those ideas I came across that was a little bit mind bending. It was a simple concept that had a lot of implications. And basically, what the authors of DFC were saying is, where they were questioning the idea of why is it that products end? Why does a useful service life come to an end, and what influences that? And really, in the sense that you live in a stable, static environment, the main reason why a product ends is because it wears out, or you lose it or break it. That's ordinary circumstances. But as you ratchet that dial up and introduce more uncertainty, you introduce things like high technology, rapid pace of technological change, or introduction of threats. And what actually influences the end of a product's life is its inability to adapt to that environment. And so the authors describe specific design techniques that can be used to better adapt a product in order to accommodate those changes in the environment. So that's a really big influence on us. And so the core idea of DFP, which really extends that to a higher capability and into a military application, that already existed. That core idea is not my idea. A couple of the things that really influenced this were, I want to mention a gentleman by the name of Dan Ward, who built a couple of frameworks and described them that called Fire and Fist, that are really emphasizing speed and simplicity, which are important design applications as part of design for principles. Another big influence really was Project Thor. This, for those folks who aren't part of Aerospace, this was an effort that really was like the gauntlet being thrown down by the DepSecDef at that time, Shanahan, who said, what can we do given this threat environment to make a more agile space enterprise and to begin to outpace the threat? And so a lot of really smart people got together in Aerospace as part of this kind of giant IPT to tackle this. And a lot of those ideas were infused into DFP. And then finally, I'd say really my day-to-day job, which since I joined Aerospace has been primarily involved with enterprise architecting and trying to tackle the wicked problems of developing a agile space enterprise. Being around all those smart people also has influenced this as well.
Right. So you're talking about like a shift in space architectures and how to design them. And this is going to require kind of a culture change as well, right? But what we've been working with is systems engineering. And now you're talking about the competitor to systems engineering and improvement. How are these things different? How is DFP and systems engineering differ?
Yeah, that's a really great way to frame the problem, and is honestly the rhetorical device I used in the paper, even from the title, where the title is Principled Design, which is a stand-in for systems engineering, versus designing for principles. And I highlight all the differences and try to explain in what ways systems engineering is currently failing us to some extent and what needs to change. And so a good way to think about this is contrasting the two. And so one of the biggest differences, one of the most fundamental differences between DFP and systems engineering is their treatment of uncertainty. So DFP thrives on uncertainty. The more uncertain the environment is, the more justification there is for making those investments in flexibility and adaptability and agility, and even being able to accommodate the world we see now, which is massive complexity and emergent properties. All of those kinds of things tend to be hated by the traditional systems engineering approach, especially as it's implemented in the Department of Defense. Systems engineering at its core requires this stability, particularly with requirements. Every part of the process, as we walk through the V, we deal with requirements, the top level requirements, we decompose them and allocate them, and we test them all the way through this process. But if anything changes with that requirement baseline, it just wreaks havoc with everything. I mean, what is the single worst nightmare of most systems engineers? It's requirements creep. It's changing those requirements such that all that work
Right.
is potentially disrupted. So DFP actually accepts those requirements changes and can deal with them much more effectively. So that's a really big difference. And part of that involves the strategic focus that DFP brings to this. And so when you say something like, and this is potentially controversial, we need to get rid of requirements or minimize them or use objectives instead of requirements. Maybe a less contentious way to think of that is, whereas systems engineering is largely focused on near-term known requirements, DFP prioritizes longer-term, currently unknown requirements, and being able to meet those recognizes that requirements change over time. So I think
So
a good way. Oh, go ahead, Alli.
I was going to say, hopefully the systems engineers in the audience have their, their minds open to this new way of thinking and not wondering why you are so out against systems engineering.
Hopefully, I mean, I know that, yeah, as a systems engineer myself, and having grown up with it and embraced it and using so much of systems engineering and appreciating what it can do, I'm a fan in a lot of ways. But hopefully, what the thoughts that I'm bringing forward today aren't in any way viewed as some sort of betrayal. But if they are to systems engineering community, honestly, probably it would take a long time for them to get together and come up with a plan that they would all agree on. So I'm probably in no danger. Um, Maybe this would be a good time also to talk real quickly about the three major pillars of DFP. The first one is don't be obsessed with requirements. The second one is keep the big picture in mind. And the third one is embrace and understand uncertainty. Now, those are the three that I talk through in the paper, and everything is kind of built around that framework and what those things mean. There's also a fourth one I snuck in there called Go Fast that maybe we'll be able to talk about it a little bit later.
So with programs getting funded at the, for these specific requirements, the whole system being based on funding specific programs, with your framework, do we begin to change that at kind of the highest levels of leadership, or are we trying to work bottom up? Where do you approach this first pillar with requirements?
Yeah, first pillar, don't be obsessed with requirements. And the best answer always is you probably approach it in multiple ways, but fundamentally what has to change is that top level piece. It's the biggest problem where we're so obsessed with requirements. Systems engineering and the structure that we're using right now for requirements capture and decomposition is inherently very rigid. The decomposition process is fairly flawed in the sense that when you deal with complexity, reductionist techniques like decomposition have a tendency to fail, to optimize the wrong thing. And so, we're seeing the problems with systems engineering right now, and we all should have some concerns about this. It has a lot of demonstrated successes, but we're not seeing the outcomes we want in terms of rapid development of effective capabilities as part of an enterprise. So, side by side again, systems engineering, when it thinks about requirements, it'll ask a question like, do we have all the requirements we need? Thinking about everything and really carefully capturing all the pieces and being very aggressive about those requirements. DFP switches the question around to, do we need all the requirements we have? How can we keep this simpler? How can we address some incremental capability now? And so ultimately, the three main messages of the first pillar, don't be obsessed with requirements, are let's have fewer requirements, make sure they're the ones that really matter. And when we can, let's try to use objectives instead of requirements, because that opens up the trade space tremendously and promotes a more incremental approach to capability development. And then number three, let's get the right type of requirements instead of just the technical performance requirements. Let's make sure that we account for non-functional requirements, which account for that ilities perspective, the agility, flexibility, survivability kind of stuff.
It's really hard to keep the programs from, or high level people from, giving up their grip on these very specific requirements and taking it to that bigger picture. But you just mentioned non-functional requirements. Can you give an example of what that is?
Certainly. It's a good question because there's not perfect consensus in the community what constitutes a non-functional requirement versus a functional requirement. So in general, what I mean is that a non-functional requirement is going to be something that is, like its name sounds, not focused on the function of the system, not what it does, but how it does it, especially as part of a larger perspective. So generally, NFRs are system-wide architectural attributes, or they're called quality attributes oftentimes, or even just for short, the ilities, because most of them end in that suffix of survivability, agility, flexibility. But resilience would be another example of an NFR that doesn't have that suffix. So it could be a lot of different things. So to use an example in the space community, I'm making the distinction between technical performance requirements like sensitivity, precision, latency, and the resolution. Those are the really cool things we normally focus on that get us exquisite performance. What Design for Principle says is we need to elevate the importance of the ilities to make sure that we're also accounting for not just the technical performance, but for instance, the survivability of that performance throughout the spectrum of conflict.
So if you can really enable that, that allows the lower level programs to really actually innovate with solutions as well, right? If you're only keeping these capabilities as actual things that you need to meet, it just opens the trade space. So that's great. So in the paper, you mention non-functional requirements, and that means real changes. So can you give an example of, in reality, what needs to happen to start implementing that?
Trade-offs. So it always comes back to trade-offs, and it's a question of what we prioritize, especially in an uncertain environment. So exquisite performance is great. It's needed, but it has to work with the rest of the enterprise and survive past day one of the war. Otherwise, it's, to use General Hyten's term, it's a juicy target, and it doesn't do us any good. So we've got to find the right balance between performance and survivability. And what that's going to mean in reality, in practice, is that when we go to enhance survivability, we're going to have to sacrifice some performance. So we may have to dedicate some swaps, some size, weight, and power, some portion of that satellite platform, for instance, to be dedicated to protecting that satellite. Maybe there's a protection payload. Maybe there's a sensor that helps warn of threats. Maybe there's more fuel on board. All of those things are good to help with survivability, but are necessarily going to have some performance offsets that we have to be willing to accept as part of larger enterprise solutions to keep the bigger picture in mind.
Okay, so let's switch gears a little bit and start moving into topic 2, which is the second pillar, keeping the bigger picture in mind. So Erin, can you take us through that pillar?
Sure. So I think that systems engineering, especially again as it's being practiced in the DoD, has begun to promote a lot more local tactical thinking, not keeping the big picture in mind, because everything tends to be decomposed as something to be managed locally, because there is so much complicated matter that we need to account for. And that's understandable, but I think it causes us to lose sight of the big picture and begin optimizing the wrong thing, that's one of the problems with decomposition in a really complex environment. So yeah, you see this with requirements. It starts right at the beginning with the requirements process and the top level requirements that get allocated to the service in the form of a JSIDS approved capability development document. That CDD typically is system specific. They already have a system solution in mind. And so the capability development process that we have going on is born stovepiped. We destroy design trade space right at the outset. And we force this siloed thinking into the process. We have to overcome that because we know right now in the way that we need to fight wars and be effective as an enterprise, everything's connected, everything is networked. We know siloed approaches tend to be more fragile. We know the most effective way to deliver capabilities is through this inherent strength that we get from an interoperable and highly integrated architecture. None of our processes support that. The requirements process, nor the funding process, which is a whole other good topic to have, they're locally and they behave as if these things aren't connected. So honestly, this isn't in any way systems engineering's fault for some of the bigger picture problems, but DFP tries to account for that as part of its methodology and make sure that we are keeping the big picture in mind right from the outset.
Erin, let me ask you, if you had an organization that was ready to think about the bigger picture, which is one of these pillars, but not ready to reform how they handle requirements, how far are they going to get? Can you touch on that a little bit if they're still kind of close holding the survivability of like single systems and silos?
Yeah, honestly, probably not as far as they need to. There's so much in a relationship between the pillars. I think that you've got to really commit to all of them for this to work in its entirety. It doesn't make sense to think about the bigger picture but keep requirements small. It doesn't make sense to think about how to reduce the requirements and focus on the non-functional requirements if you're not going to really treat uncertainty the way it needs to be treated in this current environment. So I think you've really got to work on them in tandem.
What about the architectural implications? Can you explain that a little bit for this second pillar?
Yeah, I think if you really take the idea of keeping the big picture in mind to its natural conclusion, it has some pretty significant implications to how we do architecting and changing the focus from the traditional mission areas to more of the cross-cutting kind of areas. So as opposed to the verticals, the satellite communications, the missile warning, those are absolutely critical capabilities that we provide as a space force, the joint warfighter, and we have to do that. But if we're going to deliver an integrated enterprise, we need to have greater focus on those horizontals, those cross-cutting functions and capabilities that everybody relies on, and think about how we can provide those as a common set of capability utilities or even architecture as a service that allows us to overlay verticals as needed. We can put in smaller bits, smaller investments of mission unique pieces into this architecture. And that provides a lot more inherent flexibility to be able to adjust those missions, again, as circumstances warrant, and maybe even whole new mission sets that we don't foresee today.
So that flexible architecture is key for your third pillar, embracing and understanding uncertainty. And that section really gets into some of the current things that are done in systems engineering, like risk management and functional availability, which are two things that I was exposed to. But you really kind of dismantled those in the paper. And can you kind of talk about this third pillar and how we can better set ourselves up for uncertainty?
Sure. So those are definitely a couple of sacred cows in systems engineering, and they're both related to this third pillar of embrace and understand uncertainty and what that really means. So let's start with risk. Again, there's this narrow view of the concept, overly narrow, that prevents us from optimizing for the enterprise. It's pretty tactical, and it involves things like a program. We talk about risk in the context of an individual system, and we look at the cost, schedule, and performance. So what that does is potentially distort the right thing to do to optimize at the enterprise. So imagine we have some new threat that emerges, nobody anticipating, and we've got to do some sort of quick turn change to our architecture in order to more effectively respond to that. Maybe what we want to do is start a series of high risk programs that bring in some new technology to counter this threat. But every one of those programs, viewed at from the program lens, is very high risk. Maybe it has a 50% chance of failure. Looking at it through that lens, these are all too high risk to invest in. But if we look at it from the enterprise perspective, and if in fact each of these programs is independent in terms of its solutions, the chances that one of them will succeed and counter this threat is actually well above 90%. So it's important that risk be considered and evaluated at that larger perspective, keeping the big picture in mind for what the uncertainty means. So that's one aspect of how risk needs to change. Another part is focusing on the right thing, keeping the big picture in mind and also keeping the true objectives in mind. Our business is not to deliver systems. Our business is to deliver capabilities to the warfighter. And so when we focus on cost, schedule, and performance, that's good for the perspective we have, but we have to also make sure that we incorporate the perspective of operational risk, meaning we need to account for the fact that from the operator's perspective, they may not want to wait 8 years for 100% capability. If there's an option to get 50% capability in 1 year, that may be the right thing to do. And we need a better means to balance those different considerations as part of a more strategic perspective on what risk is. Another obvious piece and problem with risk is the name itself. We talk about risk management as if that's all we need to think about is the downside of uncertainty. The fact is there's upside of uncertainty, there's opportunity, and that has to be accounted for as well as part of a larger consideration of the spectrum of uncertainty. We need to think about, the downsides, but also the upsides, and to think about them in a discrete manner as if they don't influence one another is way too myopic. We need to look at them all together at once. And then ultimately, the math has just become silly on these things, both how we do risk and the risk matrices and the multiplying probability times consequence and the functional availability and all the simplifying assumptions that have gone into that. They're actually getting to the point where they are promoting bad decision making. And that's also something that we need to account for, I think.
Right. And you also said that I heard in there programs or customers don't want to wait. The warfighter doesn't want to wait 8 years for the system to show up. So you have a secret fourth pillar on going fast. And that is going to be in your second paper or your current research. Can you talk to that a little bit? Why'd you throw that in?
Yeah, absolutely. Sure. So the paper that's published talks about 3 pillars. That's how it's structured. And that's how I describe DFP in terms of what it is, how it's different from systems engineering. In the current research, what I want to describe in a lot more detail is the so what. How do we do this? So the first paper is really the academic. What does this look like? What is the justification? The second paper is more practical. How do we actually implement DFP? What does that look like? What recommendations? Who does what as part of the Space Force if we're going to pursue this alternate capability development approach? And as part of coming up with those specific sets of recommendations, I realized I was missing a whole other pillar. There was another major theme of DFP that just permeated everything. And so I didn't call it out explicitly. And so I tried to correct that in my current thinking. Really, there's this fourth secret pillar of go fast. And go fast is so important to so many aspects of DFP because this is the other way that you can respond to a changing environment. You're going all the way back to where we started, this idea of design for changeability, design for adaptability. One way to do that is to use certain design principles to extend the life of a given product, of a given system. But another way to do it is to plan for frequent upgrades, plan for iterative approaches so that you can better respond to new circumstances. And so going fast gets at that. And the idea of going fast really is to break this terrible thing that I call the stagnation cycle of space acquisition.
Can you get into that a little bit to explain to the audience what you mean by that?
Sure. So that's my term that maybe doesn't resonate with folks, but I'll bet they recognize the concept. And it was also called the vicious cycle of space acquisition by Polakowski and Lavero in a paper they put together. And what it really gets at is this idea that our conservative approach and prioritization of exquisite performance creates this negative feedback loop where systems get bigger, we are lower risk. They're completely intolerant of any new risk and change. They start to cost more, and the schedule extends, and all that begins to feed on itself. So that as it gets bigger, consumes more resources, it starts to be the only game in town, and so more requirements get thrown at it, and it gets even bigger. And in order to justify all of the money being thrown at it, it has to become even more reliable, which costs more money and takes more time to achieve that. And then, worst of all, it essentially infects everything around it, that entire ecosystem. So if you have a satellite that is this huge monster that has to do everything, you also have to make sure that the launch system is now 5 nines reliable because we can't afford to lose this system. And the ground system has to be perfectly reliable. And now it has to have a whole architecture to protect it. And so this is the stagnation cycle that going fast tries to overcome and replace with what I call the celerity cycle. And all of those things get flipped so that we create a positive feedback cycle where we can go fast and everybody else wants to go fast. And everybody's okay with taking risk. And it's not a big deal if one particular effort fails because it was a targeted set of small requirements. It was potentially high risk, but from the enterprise perspective, we had several other efforts underway as well. And so it's okay that we had these failures. And now we free up additional resources to compensate for those failures. And everybody's in this ecosystem of constant innovation. And so that's why the fourth pillar of go fast, I think, is really important. And I probably should have made a greater point to that effect in the first paper.
So is the DoD space enterprise ready to tackle some of these deep issues that you mentioned and these pillars?
Good question. I wish I knew. I think it again comes back to this idea of an inflection point. If we're ever going to do it, it's now. We have an incredible opportunity to reevaluate our fundamental assumptions about a capability development approach and try to correct some of the problems we're seeing with systems engineering in this increasingly uncertain environment. So obviously, this is a major paradigm shift. What's being proposed here in terms of completely rethinking requirements, completely rethinking how we deal with uncertainty, the whole design flow, the abandonment to some degree of the V process, which is highly sacred. In order to have any sort of meaningful discussions like that, we're going to need to do some more vetting. We need some more eyes on this, where smart people are evaluating whether the DFP concept really has merit and is something that we may want to pursue. But we've also got to move fast. This is the whole idea of having a smaller space force, that it can be more agile and we can take some chances. I think there's a great opportunity here to move out quickly and potentially institute some sweeping change. So if we get that peer review, we get people looking at this, that's important. But we also need them to look at how realistic some of these implementation recommendations are. In the current research that I want to publish, it talks a lot about specific recommendations for specific actors to go implement DFP, what that means on an enterprise basis, up through OSD and headquarters, all the way down to programs and people, what we need to do to implement DFP. I think we're going to have to really think through that carefully about what's realistic. Ultimately,
The Space
There are a
Force
lot of
is,
Go ahead, Alli.
sorry, the Space Force is looking to be a digital service, right? And that's part of this as well.
Perfect. Yeah. So the Space Force is ready to embrace change. That message is being consistently communicated in every place that I see. And one of those areas is this vision for a digital service. That's a huge part of making DFP work, because design for principles is all about this idea of managing complexity at a level that systems engineering can't. But that's going to require some help from techniques like digital engineering. I know also that, I have a relatively narrow view of the world. There's lots of stuff going on in terms of Space Force, but I know they have a capability development IPT that is reevaluating capability development strategies. I know that there's the acquisition overhaul that OSD is looking at and trying to get Congress to buy into. There's a whole lot of stuff going on where there's an opportunity to look at things differently right now.
Great, Erin. Well, is there anything else that we haven't hit on that you wanted to go back to?
Maybe there's one thing that's worth discussing a little bit more, and that's this idea of complexity. Talked about that a little bit and how that's potentially a game changer, but part of the audience may not really appreciate the subtleties in language there. I think to most of us, we use the words complexity and complicated as synonyms, but to people in systems theory and operational research, there is a huge distinction between a complicated system and a complex system. And just as a quick explanation of that, a complicated system could be something like the space shuttle. It's super complicated, but it's subject to standard decomposition efforts. We can figure it out. We can repeat that process. In a truly complex system, we have so many more interactions, and they are so difficult to model and capture those things that the entire system becomes nonlinear. It's non-deterministic. It's such that the inputs do not consistently produce the same outputs. So a classic example of a complex system would be like a local thunderstorm. We can't, even if we know everything and can model it, we can't predict the complete output and behavior of that system. So complexity is becoming more and more a fact of life. And systems engineering was well suited and continues to be well suited for complicated systems, but it's not a good match for complex, because complex is this new environment where we start introducing that worst category of requirements that Donald Rumsfeld talked about, unknown unknowns. Those arise routinely in complex systems, and that's a category of input that systems engineering is just really bad at. So fundamentally, we have to come up with a new capability development approach that can account for changes in requirements, uncertain environments, and complex situations. So whether we adopt DFP or something else, I guess my takeaway message for everyone is we have to recognize that there are some fundamental weaknesses in systems engineering, and we need to figure out a way to address those at this inflection point.
Yeah, Erin, I'm really excited to see this conversation happen more in more places, and to kind of for this framework to take hold, to see what comes next with this. So let me thank you for having me on today, and appreciate you letting me be part of this conversation and quizzing you a little bit for our audience. So any last final thoughts?
Thank you, Alli, and thanks to CSPS for hosting us.
Absolutely. So let's hand it back to Rebecca.
Thank you, Erin and Alli, for that great overview of space design flexibility. And thank you so much to our production team, James Liggins and Sarah Panoni, located in the Los Angeles area. As always, check us out on Twitter. We're at #TheSpacePolicyShow, and sign up for our latest news alerts at aerospace.org/policy. Tune in next week for a panel discussion on how government can leverage the innovation and R&D coming out of academic institutions, featuring leaders from Purdue, Stanford, and AFRL. And until then, take care.